Under raking afternoon light, the limestone surface reveals something that should not exist. The T-pillar stands 5.5 meters tall, its horizontal crosspiece weighing an estimated 3 tons, carved from bedrock using what archaeologists insist were flint tools and hammerstones. Run your hand across the surface. It is not just smooth, it is planar, flat to within millimeters, across 4 meters of vertical stone. The official story places this at Gobekli Tepe, carved by pre-pottery Neolithic hunter-gatherers around 9600 BCE, before pottery, before agriculture, before metal. But here is the crack. Flint hardness versus limestone abrasion rates do not match what laser scans reveal. The surface finish is too controlled, too uniform. If we have misunderstood the stone shaping technology here, the entire timeline of early Neolithic capability shifts. And that is just one pillar. There are dozens. If this level of planning existed here, what else are we misdating? You approach the excavation and the scale hits first. The central pillar rises 5 meters from the ancient floor, T-shaped and massive. The horizontal arms of the T stretch nearly 2 meters across, carved from the same monolithic block. Weight estimates put this single pillar at 15 to 20 tons. Your eye tries to find irregularities, waves in the surface, bumps from rough shaping, but the stone presents near perfect planes under the harsh sun. The official narrative is straightforward. These pillars were quarried from nearby bedrock outcrops, shaped with hammerstones and flint tools, then dragged to the site and erected. Simple percussion work, just patient and repetitive, the kind of labor that takes time but no special knowledge. But achieving planar faces over 4 meters in height with handheld percussion tools requires something beyond patience. Every strike of a hammerstone creates micro fractures and uneven divots. The surface should show chaotic pitting, gradual smoothing, accumulated error. Instead, you are looking at geometry. The flatness is not approximate, it is measurable. Laser scans confirm deviations of only a few millimeters across the entire vertical face. That is not luck, that is control. Look at the pillar's edges where the vertical shaft meets the horizontal arms. The transition is crisp, almost architectural. The sides of the pillar run nearly parallel from base to top, deviation measured in centimeters, over 5 meters in height. Shadow lines at dawn trace these edges without wavering, straight as surveyor's marks. The accepted explanation relies on gradual pecking and smoothing. Strike the stone, check the surface, strike again, smooth with abrading stones. Repeat for months, but error accumulates. Each strike, slightly off angle, compounds into waviness. Without reference grids, without measuring tools, maintaining parallel faces becomes a probability problem. The more you work, the more drift you should see. Yet here the geometry holds. The pillar sides deviate less than 3 centimeters across their full height. Stand at the base and sight up the edge. The line does not wander. Engineering teams have noted this. Maintaining such tolerances with percussion methods requires constant verification against a reference standard. What reference? When the builders supposedly had no metal straight edges, no plumb bobs, no surveying equipment beyond simple tools. The symmetry is clear. The question is not whether ancient builders were skilled, it is how they maintained control that even modern stonemasons would find challenging with hand tools. Now step closer to the relief carvings. A fox wraps around the pillar's face, its body carved in shallow relief, depth consistent at 10 to 12 millimeters across the entire form. Internal corners where legs meet bodies show radii under 1 centimeter. Sharp, deliberate, uniform. The standard account attributes these to flint, chisels, and patient abrasion. Flint can work limestone, no one disputes that, but flint edges chip, dull, and fracture under repeated impact. The volume of material removed from these reliefs is substantial. You are not talking about scratching the surface. You are talking about carving away cubic meters of stone across dozens of pillars, maintaining depth uniformity within millimeters, preserving crisp internal corners that should round out as tools wear. Recent scans have documented relief depth variation of less than 2 millimeters across multi-meter carvings. That is finish work precision. If you are constantly replacing worn flint edges, each new edge has a slightly different geometry. The carving should show micro variations, stepping, inconsistent depth where fresh tools bit deeper. but the reliefs read smooth under scanning light. Either the builders had an unlimited supply of perfectly consistent flint tools, or the finishing technique was more controlled than percussion and abrasion suggest. The tool marks we would expect to see are not there. Walk to the quarry site, visible on the ridge above. Here is where the pillars originated: limestone bedrock, with extraction trenches carved around proto-pillars still attached to the living rock. The trenches are narrow, half a meter to 1 meter wide, just enough room for workers to strike downward, separating the pillar from the bedrock below. Archaeologists propose the pillars were freed this way, then shaped and placed before transport. Makes sense. Work the stone where it sits, then move it once. But physics intrudes. A 15-ton pillar in a 1 meter wide trench has no turning radius. You cannot rotate it. You cannot tip it to check the underside. You are working in a slot barely wider than your shoulders, trying to shape all four faces of a multi-ton monolith without being able to access more than one side at a time. The geometry we see in the finished pillars requires seeing the whole form, maintaining symmetry between faces. That is hard when you cannot even walk around the object. Either they possessed extraordinary spatial visualization, carving blind and getting it right, or the shaping happened after extraction. But moving rough 20-ton blocks through narrow quarry terrain introduces its own problems. Either scenario has physics, costs. Both cannot be easy. Examine the edges where the T-arms meet the vertical shaft. Some of these irises, the lines where two faces intersect, retain sharpness under 5 millimeters. Trace your finger along the transition. It is nearly knife edge crisp in places. That is after 11,000 years of weathering. Limestone is relatively soft. Mohs hardness around 3. Windborne dust, thermal expansion, rain and biological activity all slowly round edges. The standard archaeological explanation acknowledges this. The climate in southeastern Turkey is relatively stable and dry for much of the year, which helps preservation. Fair enough. But weathering rates do not pause selectively. Edges erode faster than flat faces because they have more surface area exposed to environmental attack. Over 11,000 years, even in stable climates, you would expect more rounding. Modern limestone structures in similar environments show measurable edge degradation over just centuries. Yet here, some edges look almost fresh, others on the same pillar at the same elevation show more rounding. The erosion pattern is inconsistent within identical stone layers. That suggests differential exposure, some edges protected, others exposed, or different ages of carving. If the pillars were all carved, erected, and buried in the same phase around 9,600 BCE, erosion should be relatively uniform. If the sharp edges existed when the structures were intentionally buried around 8,000 BCE, as excavation evidence suggests, then they should be even sharper now, having spent most of their existence protected underground. The weathering evidence does not quite fit a single-phase timeline. Consider the transport problem. The largest pillars weigh up to 20 tons. They were moved from the quarry ridge to the circular enclosures over distances ranging from 100 to 500 meters. The official explanation is wooden sledges, ropes, and manpower. This implies hundreds of workers dragging the stones across the landscape. The physics gets tight. 20 tons distributed over a sledge creates significant ground pressure. Neolithic soil in the region, with no paving and no prepared roadbeds, is relatively soft. Engineering simulations of sledge transport over unprepared ground show significant rutting under heavy loads. Dragging a 20-ton object on wooden runners will dig trenches unless the ground surface is somehow stabilized. No evidence of prepared stone roadways has been found at Göbekli Tepe. Either the builders used temporary surface preparation, such as wooden planking or compacted fill that has since disappeared, or transport happened over frozen ground, or some other method was employed. All are possible, but each solution adds complexity to a culture that is usually described as operating at hunter-gatherer organizational levels. And there is the road itself. The terrain is not flat. Dragging multi-ton stones up even gentle slopes requires managing the gravitational load. Rope tensile strength becomes critical. Plant fiber ropes of the period could handle loads, but failure margins tighten fast when pulling 20 tons uphill. The transport happened, the pillars are there. The question is, what infrastructure supported it? Roads, ramps, stabilized surfaces, rope anchors, and specialized tools would all have been physically necessary, yet they are invisible now. That level of logistical planning does not align easily with small mobile forager groups. It suggests project organization at a different scale. Each pillar sits in a socket carved into bedrock, 30 to 50 centimeters deep. The fit is precise. The pillar base is shaped to match socket walls with minimal gap. You can barely slip a finger between stone and bedrock in places. The standard explanation is that earthen ramps were built around the socket. The pillar was dragged up the ramp, then tilted into position using ropes and leverage. Manpower and patience, simple mechanics. But the tilting moment is substantial. A 5-meter pillar weighing 15 tons, tilted from horizontal to vertical, creates enormous leverage forces. The pivot point, the edge of the socket, experiences crushing loads. The rope attachment points high on the pillar must resist the full weight multiplied by the lever arm. Engineering estimates suggest you would need rope tensile strength well beyond typical plant fiber capabilities, or massive redundancy, dozens of ropes sharing the load. Coordination becomes critical. If ropes fail asymmetrically, the pillar pivots sideways, potentially shattering, and the lift angle is unforgiving. Tilt too fast, and momentum carries the pillar past vertical. It topples into the socket and cracks. Too slow, and the static load exceeds rope capacity. You need controlled speed, which means friction braking, which means even more rope systems. The pillars stand upright, undamaged. The erection was successful, but the margin between success and catastrophic failure in the final lift is measured in degrees of arc and rope load distribution. That is engineering precision, not trial and error. Ancient builders clearly solved this problem. The question is whether simple ramps and plant fiber ropes fully explain the control required, or whether some element of the technique remains unrecognized. Step back and compare the central pillars to the surrounding enclosure walls. The contrast is immediate. The pillars have planar faces, parallel edges, and uniform relief carving. The walls show rougher stone, irregular coursing, and cruder joints. It is like seeing two different construction traditions in the same space. The standard interpretation is different work crews or different construction phases. The pillars were the sacred focus, receiving maximum effort. The walls were secondary, built quickly to define space. That is reasonable. Craft quality often varies by importance, but the technical gap is wide. The skills required to shape the pillars, maintaining geometry, carving reliefs, and achieving a refined surface finish represent sophisticated stoneworking. The wall construction looks comparatively rudimentary. It is not just less effort, it is a different capability. Some researchers suggest the pillars may predate the enclosure walls. Perhaps the pillars existed first, were already ancient focal points, and later builders constructed walls around them. That would explain the craft mismatch. The wall builders were not trying to match the pillar quality because they could not. They were incorporating older monuments into new sacred spaces. This remains speculative, but the visual language is inconsistent. You can see it standing in the enclosure. The pillars speak one technological dialect, the walls another. Either the same culture had wildly variable skills depending on task, or the construction timeline is more complex than a single building phase. If the pillars are older than the surrounding structures, even by centuries, the entire site chronology shifts. What looks like a unified Neolithic temple complex might instead be a landscape where later people built around earlier monuments they found and revered. The stones do not wear labels, but they do not look contemporary. Examine the main pillar faces one more time, this time looking for tool marks. Percussion shaping should leave diagnostic scallops, curved depressions where hammerstones struck. Even after final smoothing, these patterns usually remain visible under raking light. They are the signature of how the stone was worked. On Gobekli Tepe's pillars, consistent percussion scallops are largely absent from the main planar faces. The surfaces are smooth, but not in the way hammered stone should be smooth. The expected micro-topography is not there. The official explanation is 11,000 years of erosion erased the tool marks. Weathering smoothed the surfaces, removing evidence of the original working methods. That is plausible. Limestone does weather. But here is the problem. The relief carvings on the same surfaces still preserve fine detail. Animal figures retain depth, uniformity, internal corners stay crisp, and shallow features remain legible. If erosion was aggressive enough to completely erase percussion marks from the flat faces, it should have degraded the carved reliefs as well. Both surfaces are the same stone, the same age, the same exposure history, yet one shows detail preservation, the other shows mark erasure. That is selectively convenient. Either the erosion was somehow differential, flat faces weathered more than carved surfaces, which does not align with typical erosion patterns, or the tool mark absence has another explanation. Perhaps the final finishing technique left minimal marks to begin with. Perhaps some surface treatment we do not recognize was applied. The lack of expected tool signatures raises questions. We know the stone was shaped. We can measure the results, but the process that left these specific surface characteristics remains unclear. Erosion is real, but invoking it only where evidence is missing starts to feel like a placeholder. Consider the burial itself. Around 8000 BCE, the enclosures at Göbekli Tepe were intentionally filled with rubble and dirt. Massive labor went into burying these structures. Thousands of tons of fill were carefully placed. The pillars, the carvings, the whole complex were deliberately covered. The archaeological interpretation is ritual closure. The site served its purpose, and the community chose to seal it ceremonially. It is a powerful statement about changing belief systems or social structures. But think about the logistics backward. These pillars represent enormous investment, quarrying, shaping, transport, erection, months or years of labor per pillar. Dozens of pillars across multiple enclosures. Then after all that work, after using the site for perhaps 1,000 years, they buried it all. That is a strange decision unless the pillars themselves were already ancient when the burial happened. If the builders of the enclosures were working around monuments they inherited, pillars they did not create but revered, then burying them makes different sense. You are not discarding your own work. You are sealing something from an earlier time. The fill layers contain broken tools, animal bones, worked flints, debris from the site's active use. But they also show deliberate placement, not random dumping. The burial was methodical. Here is the uncomfortable question. What if the people who buried Gobekli Tepe did not fully understand what they were burying? What if the pillars were already mysterious to them? Relics from an earlier period they could no longer replicate? The timeline might be nested. Pillar carving in one era, enclosure construction in another, burial in a third. Each phase separated by centuries or more. The stones do not carry dates. Radiocarbon can date organic material in the fill, not the limestone itself. We are dating the burial, not the building. Look closely at the pillar surfaces near ground level versus higher up. Return to that perfectly straight edge on the main pillar. Sunlight at a low angle traces an unbroken shadow line down 4 meters of stone. The deviation is centimeters across the entire height. You can measure it with lasers, document it in scans, and verify it with photogrammetry. The precision is real. The measurements do not lie. We can describe what exists. We can quantify the tolerances, calculate the masses, and model the logistics. What remains uncertain is the full picture of how it was achieved. The complete toolkit, the organizational structures, the knowledge systems that made this possible 11,000 years ago. The official story of flint tools, manpower, and patient labor explains some of it, maybe most of it. But when you stack the constraints, including geometry control, surface finish, transport logistics, erection mechanics, and regional coordination, the simple version starts feeling incomplete. This does not prove alternative timelines. It does not validate fringe theories. It just means the story is more complex than introductory texts suggest. Ancient builders possessed capabilities we are still working to fully understand. The stones stand as evidence of what they achieved. The methods, the organization, and the knowledge transmission remain partially visible and partially obscured. We can measure the line. The straightness is documented, verified, undeniable. We just do not know who first drew it, or what else they knew that the standard story has not captured yet. The investigation continues. The stones wait, patient, holding their secrets in measurable precision.